you see, if you have a surface like this, it's defined as 2 plus 2x plus 2y minus x squared minus y squared, you can see the maple picture of how it looks, and you can get the feeling from the appearance of that there probably is a relative maximum, local maximum, perhaps an absolute maximum z value that the surface that you reach if you're on that surface. So what the section 14.7 is about is how to use partial derivatives to determine whether there is a maximum point, and if there is, to find it. If you turn the thing upside down, the surface turned upside down then, in the same way, would lead you to talking about whether there's a minimum. And in general, if you think about, as I mentioned last week, if you think about flying across eastern Oregon or open country like that where you can see volcanic peaks, volcanoes that are peaks, you can see pits, the craters, and you can see saddle points. So back to the example, you see that you could, in the case of this particular problem, decide algebraically about whether there is a peak or a pit, and if so, where, even if you didn't have calculus. If you look at the calculus approach, you want to find local, you can use the word local, you can use the word relative, maximum, minimum, or saddle points, peaks or pits or saddles. And so what we use is what people call a discriminant. You can use a letter name for it, which is the product of the second partial derivatives minus the product of the mixed partials. In other words, this. These are the second partials and these are the mixed partials. You remember that the mixed partials will always be equal for anything that's in our book. And it turns out that if the discriminant is negative at the point that you have to determine that we call a critical point, this critical point where you're going to get x and y values to substitute into this expression and then decide whether it's negative or 0 or positive, that point would be called a critical point, and it, like in first semester calculus, and you get it the same way. It's where the first partial derivatives are both 0. It'll turn out when we go back to this example, you see, and redo it here with the calculus, that the critical point for this one is this point 1, comma 1, where we ended up finding that we had a maximum. So we form the discriminant, we find the coordinates of any critical point. There could be several. You could have a surface that has a peak one place and a pit another place and a saddle another place and so on. You find these critical points by taking the first partials, partial with x and the partial with y, and solving two equations simultaneously to find these critical points. So then finally, at the critical point, if your discriminant is negative, you have a saddle. If it's 0, it's inconclusive. It's like the second derivative sign test in Math 170. If your second derivative is 0, you don't know whether you have a maximum or a minimum, or what in Math 170 you call a terrace point. And finally, if your discriminant is positive, then you notice if it's going to be positive, since this is always something you're taking away here, the only way the discriminant can be positive is when these match in sign. These would both have to be negative, so minus times minus is plus, or they'd both have to be positive. So since the signs have to match in this case, you could use either the second partial with x or the second partial with y as your sign test to choose between minimum, in other words a pit, and maximum, in other words a peak. And that's like Math 170, where you say you think of x squared, your second derivative is 2, which is positive, and you know your graph is like this, your parabola. So you have a minimum, so you associate minimum with positive second derivative in Math 170, positive second partial in this example. And it could be just as well a second partial with y. And in the same way, if you had y equals minus x squared, you have this picture. Second derivative is negative, so you associate negative with maximum. And so at your critical point, either your second partial is with x is negative or your second partial with y, because again, they have to agree if your d is going to be positive. So now, coming back to here, go back to the start, do your partial with x. So you have 2 from here minus 2x. And so your critical point will be where the first partial with x together with the first partial with y will be 0. Since this is an equation with x only, you can go ahead and solve, set that equal to 0, and you can see that that happens when x is 1. 2x equals 2 and x is 1. You do the same with the partial with y. See, you get a 2 there and a minus 2y there. Again, this equation involves only the one letter, so you can solve it. You don't have to solve it as a system. Generally, these partials will involve both letters, like in these examples here, and so you have to solve it as 2 equations and 2 unknowns. But here, it's easier because there's just the one letter, and so you get the x equal 1 and y equal 1, and that's your critical point. Then you do your second partials. Derivative of this, minus 2. Derivative of this one is minus 2. Notice they match in sign. And also your mixed partials, partial of this with y or partial with this with x, those are both 0. So your discriminant is positive. In this case, it doesn't vary with x and y, so it's positive everywhere. In general, your discriminant is going to be a function variable with x and y, and it'll be positive one place and negative another, perhaps. This one is positive, and so then you use either of these signs as being negative to tell you that you have a maximum, which is what we found algebraically by playing the game with the squares. And what you can see in the maple picture that you have, especially if you turn the page, on the back, you see where this peak actually is. this is the single sheet of paper I'm talking about. So this first example is on that single sheet of paper. And so if you look at the back side of the single sheet of paper, you see I marked with the red line where this peak would be. The reason that the maple graph, the box axes, have such big numbers up to plus 60 and down to wherever that is, about minus 50, is that when I told Maple to draw the graph, if you go back to the first side of the paper, you see I have display. You do display when you have more than one plot structure that you're trying to put together. And first there's the surface, and then the space curve, you see, is the line that I put in there just to identify where this maximum is at 1, 1. And it's because I did t equals minus 0 to 60. It's because I gave it that much of a interval for the t. That's why the picture shows so much rise on the vertical and the picture on the back. So anyway, you can see the idea of the surface and that there is a maximum there, and by putting in the red line you can see where. Otherwise it would be hard to look at the picture and see just where that is. So this is what's going on with this. Now, the other handout, the one that's stapled together, did everybody get this? Did you guys get one that's stapled together? Okay. So, let's look at some problems that are drawn in it. So here's problem 2. And so I do my partial, I'm after the critical point, so I do my partial with x, and you see I get 2y, and I get minus 10x, and I get a 4 from over here. Notice this involves both variables, so you're going to have to solve this now as 2 equations and 2 unknowns, which is going to be the usual situation. And then I do my partial with y, which is 2x minus 4y and 4. And so what I'm doing is solving my 2 equations. So I have, let's see, I have taken the minus 10x that's here and put it first so that I get the x's in the same column and the y's in the same column. So I rewrote the order there, and you see to get your critical point, you're solving where f, the 2 partials are equal to 0. So I moved this in the opposite order and then set it equal to 0, so that 4 then became minus 4, and then I set this equal to 0, and I have 2x minus 4y equals minus 4. So then if I take the top one times 2 and put it down there, I have minus 20x plus 4y equals minus 8. And then I take the bottom one, I copy over here and tell myself to add, okay? So this has become a Math 25 class, hasn't it? How to solve 2 equations and 2 unknowns. And anyway, I add these up, and you see I have minus 18x and here I have minus 12, so x is 2/3. Your critical points don't have to be whole numbers, of course, and they don't even have to be rational. They could be square root of 2 or something like that. And after you get the x, as you know, you could substitute into any of these equations and get the corresponding y. So I've done that. I've put that back into this one, I guess. 2/3, and then 2x minus 4y equals minus 4, solve for y. And so finally, minus 4y is minus 16/3, so I get 4/3 for y. So then, to do my discriminant, I have to do my second partials. So back to here, derivative of this with x gives the minus 10, derivative of this with, well, and then if I took this and did the partial of this line with y, I'd get a 2 from there. And that's also what this will do if you take its partial with x, and then take the partial of this with y, and you get the minus 4. So then my discriminant is the product of the second partials minus the product or of the mixed partials, or the square of one of them. And you notice these are both negative. This is positive, and the discriminant's positive. So that, and that tells you that you're looking for either for this or for that situation. And your second partials are both negative, so it's actually this situation, the peak. So you have the relative maximum at 2/3, 4/3. This means that it would have been algebraically possible to take this thing and play a game comparable to this and finally get this thing rewritten in the form of whatever the value is at this point, which I don't actually have, but it's whatever you'd get if you took 2/3, 4/3 and substituted here and did your calculation. You could then rewrite that problem as that number, whatever it is, minus a couple of perfect squares, but it might be challenging algebra to see just how to do it. It's much easier to go through the drill like this because it's like a program, and it just goes once you feed in the correct data. So this is the game that we play in 14.7, and I think it's a welcome relief. I think this is a good deal easier stuff to understand than some of the things that go with the gradients, so on. Take a look at, take a look at your handout. I believe that I have a picture of this. Problem starts on the bottom of the first page, and I've drawn the picture on the back of the first sheet of paper. This one shows up pretty well. I think that there is a maximum, although again, if you just had to look at the maple drawing of the surface without my red line, it would be hard to pick out exactly where that is in the picture. And so anyway, take a look at 3. which we have here, and we do our partials. And again, you notice that this one involves both variables, this one just involves x. So the easiest way to solve this is to set this equal to 0 first and get your x, which is -2. After you do that, you can solve this one for y, when you set this one equal to 0. So that's what I'm doing here. First I get x is -2, then I substitute there, then I solve this for y, and so I get my critical point. The problems that are in this book are comparatively easy in that they really have chosen problems where there's just the one critical point. But you see, if you have a surface where these are higher degree polynomials, then when you do your partial derivative, say if there were some cubes here, you'd have squares in here, and you'd have equations to solve that would be quadratic, or it could be higher power yet. So you could have problems where the equivalent step to this one, where you're getting your actual critical point, could involve quite a bit of algebra. And so as it is, if we take our partial of this with x, we get 2. If we take our mixed partial, we get 1. If we take our partial here with respect to y, we get 0. So our discriminant then is the 2 times the 0, so it's 0 there. So it's going to be negative, you see, because it's minus the product of two equal numbers. And the key is, if it's negative, it doesn't really matter what number it is, whether it's -1 or -4 or what. If it's negative, it's a saddle at your critical point. So then we can try and look at the maple, and you see the picture, and I've marked where the critical point would be. Again, it's hard to look at the picture of the surface and particularly see that that's exactly where you'd say is the summit of the pass. If you're thinking of a saddle like a mountain pass with a highway, the highway's going, say, east-west, and you look north-south, and the mountains go up higher than you are. But that's what the graph says it is. Well, then we can look at another of these, and then we can go on with what else is here. So this one, you notice, there's no law that says we're limited to algebraic type surfaces. So the methods apply as long as you have a surface defined by a function where you can do these derivatives. So here's one which is transcendental with the logarithms. Well, you do the same things. You do your partial with x, so you get the 2 times 1 over x, and then 0, and then you get -4 here, and then you get 0. And then you do your partial with y, so you get a 1 over y and a -1. So then your critical point will be where this is 0 and also that one is 0. Notice that this is one where you have only the one letter in your expression that's to equal 0. So you can solve separately for x and get a half. you can see that 2 divided by a half gives you 4, and 4 minus 4 gives you 0. And then in the same way, set this equals 0, and so 1 over y is 1, and so y is 1. So here's your critical point. Then for your second partial, rewrite this with the negative exponent, 2 times x to the minus 1, and bring the minus 1 down, times 2 gives you minus 2 over x squared. And your partial of this with y in the same way gives you minus 1 over y. And you notice that your mixed partials are both 0. There's no y here, and there's no x here. So you're at the critical point where the y is 1, this is going to be negative, and that's going to be negative, so the signs match, and so your d value, your discriminant, is going to be positive. And the fact that it's 8 doesn't particularly mean anything any different than if it were 4 or 16 or something. It's just that it's positive. So you're back to this situation, and so either one of the second partials is negative, and so you're looking at this situation. So you have your maximum then at your critical point, and if you actually want the function value, I think in this problem the book wants you to actually say the maximum value, which is the value then at this point that this will take. So you feed the half back here for the x, and the 1 back here and there for the y. Remember, log of 1 is 0, and so your maximum is a negative number, but it's the least negative, so it's like minus 1 is greater than minus 2, and so on. And I think we have the picture. If you look on the back of the second sheet of paper, and I also did the maple with problem 30 in the picture for it. So now what we're starting next, what the rest of what's on the board, is chapter 15, section 1. If you look at the course schedule, I had 15.1 and 2 to do tomorrow, but I think it's better to do this and 15.1 today and have all of tomorrow for 15.2. It's a good deal harder than 15.1, and a good deal harder than this. This is not particularly difficult to do, although it's rather interesting in terms of how these surfaces look. Before I forget these things, schedule also says you should get the third test, which I'm sure you would figure out without being told. So what Stuart is after with the handout in this picture is the concept of what we call the double integral. And what we get back to is the Riemann sum idea, But now, you see, it's going to be a sum over a plain region rather than having subdivisions just along the x-axis and rectangles. We're thinking of a double sum where if we have some region like this rectangle that's supposed to represent Colorado, the reason that Stewart chose the temperature in Colorado at a particular time and date is that of the 50 states, it's the only one that's actually a rectangle, I think. So many of them have a border that's a river, and rivers don't naturally flow in straight lines, or they border on the seacoast or something. But Colorado is actually a rectangle. It's, according to Stewart, it's 388 miles. Say this, take your origin here, this would be the Four Corners Monument. So you'd have Utah, Arizona, New Mexico. And so it's 388 miles if you go east in a straight line, and what is it, 276 if you go north. So in order to present the concept of the double integral, Stewart starts with this example of the temperature at a particular time and a particular date, 3 o'clock Mountain Time, May 1st. And if you were trying to average the temperature, thinking of it as a function of x and y over the region, your average, if you remember from Math 170, for a function of one variable, the average over an interval from a to b is the integral from a to b of your function divided by the length of the interval, b minus a. So for a function of two variables, it would be whatever you mean by the double integral of the function of two variables over your region divided by the area. You see, you're moving up one dimension from length to area for your denominator and integrating a function of two variables over the region. So what chapter 15 is about is how to integrate a function of two or three variables. And so if you're doing the integral numerically, the midpoint rule, the equivalent of the midpoint rule from chapter 8 is you'd take your region and make equal subdivisions. So I made 16, say, and then I identify the midpoint of each of these rectangles. See, these rectangles are in area 276 by 388 over 16, so they're 6,693 square miles. One of these would be a nice ranch to have, wouldn't it? Especially the one that has Denver in it. Yeah, you'd have a little money. So anyway, you can, at least in my scheme, you can see there'd be a midpoint. And if you look at Stewart's contour map, you can look at the contours and kind of eyeball where the midpoint would be and kind of guess what the temperature is. So these numbers that are supposed to be the temperatures at the midpoints of the ranches are my best guess based on eyeballing the contours. And they aren't guaranteed that they're right, but this is just an example anyway, so you can use them. So what I'm doing then, you see, I'm thinking of the columns I, 1, 2, 3, and 4, going from Utah toward guess it's Nebraska that's over here. And if you go south to north, up toward Wyoming, then your J would be 1, 2, 3, 4. So I'm saying then that my numerical computation based on the midpoint rule for the double integral is the area, the common area of these 16 rectangles, the 6693. See, that's the delta A that's replacing the dA when you go to a approximation. And your denominator, the area of the region R, would be the area of Colorado, so, which is 16 times this. So finally, what it means is that you're going to do this summation and divide by 16. Your area of Colorado is 16 times the area of each of my ranches, and that's in the denominator, and then the area of one of these ranches is the delta A. So you have this number divided by 16 times it. And then you see what I'm doing for column I equal 1 is I'm summing bottom to top. So I have this number, then that one, then that one, then that one, and then I move over here and do the same thing. So I total up all those numbers and I get this number that's here, if I did it right. So finally you notice this number cancels, so then I take this one over 16 and I get 69.5 degrees as my approximate average temperature for the state at that time, that day. Okay, so this is a double integral as a setup where what we've done here is a Riemann sum, and of course the definition is that for all possible Riemann sums, if you take the limit as the number of your subdivisions becomes infinite and the maximum of any one of the areas goes to 0, all those limits are supposed to be the same, and that's your integral. The same concept as in Math 170, where you had the area under the curve and the rectangles, the number of rectangles increases and the width goes towards 0. And like Math 170, you know you've got to find a better way to work the problems, right? And that's called the iterated integral, and that's what's over there by the door. So it also goes with, guess what? The next handout. Come on, you'd be disappointed in me if you didn't get a handout. This concept that you can work the double integral as what we call an iterated integral actually goes back to Cauchy. And here's a little Wikipedia if you want to read about Cauchy. If you remember, most of you took Math 175 from me. And if you remember when we were doing partial fractions to do integrals, I talked about a method called poles and residues, maybe the name sticks, and those go back to Cauchy also. And a lot of things in the infinite series chapter, actually. Cauchy was certainly a major contributor to the development of mathematics. So, the theorem that you can get a double integral by what we call the iterated integral, although Cauchy was doing it 100 years before his time, actually was published as a mathematically valid proof by the Italian mathematician Fubini in 1907, which still, of course, is more than 100 years ago, but it certainly isn't clear back to Newton and Leibniz and Euler and those people. So the double integral and of course what will follow in a week or so, the triple integral, where you're dealing with three variables, this is much more recent type mathematics, comparatively, say. So, Cauchy, as I have mentioned, used this without ever having actually published a proof for continuous functions defined over a region where you also had continuous functions defining the boundary of the region. Whether you can do these double integrals or not depends not just on the function f of x, y, what would be like the temperature function, say, for Colorado, but also on your being able to write a formula for the edges of your region as functions that you can define, and they don't necessarily have to be continuous everywhere, but they can't be too badly discontinuous. And exactly what you can have is what's in the details of the Fubini theorem, which we aren't going to pursue, because the problems in the book are all going to be functions and boundaries that are plenty good. If everything's continuous, you can always do this. That's what you get in the problems in the book. So in 15.1 then, suppose your region is a rectangle, say like my example with Colorado. Tomorrow's class, we allow that the region doesn't necessarily have to be a rectangle, and could be various kinds of curves for the boundaries, and then that makes a tougher sort of problem. So think positive. Maybe you'll die before tomorrow, and then you won't have to hear about it, right? That's positive thinking. Okay. So if R is a rectangle, you see it's the set of pairs of numbers where X is between two numbers and Y is between two numbers, like 0 to 388 for east-west, and 0 to 276 for south to north, and for Colorado. So then our integral over the region, this is our double integral, is always something you can find by what we call the iterated integral, where what you do is integrate first with one letter, so this is partial integration. So the way this is written, you see the dy is first here. That means you'd pretend x is a constant, the same way you would if you were going to do the partial derivative, and integrate as if y is the variable and x is the constant. And then put in your limits. Remember, today's class, we're thinking rectangle, so the limits are numbers. So those would be limits on y. So then after you do this first iteration, what I'm holding my hand over, you have something remaining with x as the variable and numbers in it. You've integrated out the y in the sense that you've found an antiderivative and replaced the y's with numbers. Then you integrate what's left with x as the variable. On the other hand, you can do it the other way around. First with x, so you're integrating out the x and replacing the x's then with the limits on x, and then you have a function of y, and you do that like Math 170. So the maple command that will work a double integral by iteration is double int, as you see in the maple handout, or if you prefer, you can do it separately to emphasize the iterated idea. You can do int, whatever the function is, with the appropriate limits, and then int of the result. So iterated means that you carry out a procedure that's applied to your given data, whatever it is. It doesn't, iterated is a more general concept than just for integrals. It can be for derivatives or any mathematical operation. So whatever your procedure is, integration, differentiation, something else, you apply that to what you start with, you get a result, and then you apply the same procedure to the result. And you get another result, and you can keep on going with this until you're totally crazy, and then they let you teach math. Okay. So with the iterated integrals, what we're doing is partial integration in the sense that I was talking about here, and then work with your Math 170 rules, pretending just one variable, one letter at a time is your variable. So if you look at problem 9 in 15.1, you have this problem. And so if you focus your attention on this, with the dy, you're going to do the integration with respect to y then. Okay, so what I would do here to separate things out is use the rule for exponents. When you multiply product and powers, you add the exponents. So if you have exponents added, you can factor into whatever is your base, which is e in this problem, with the 2x in one factor and the y in the other one. Because you see, if you had started here and were multiplying, you'd add exponents, and that would take you back here. So then you can essentially move the e to the 2x from here across over into there, and just look at e to the y between the limits on y. So this is what I'm trying to indicate as what you're doing in your mind. So the integral of e to the y is still e to the y, and then you evaluate between the limits on y, just like Math 170. That gets you e to the log 5, which is 5, minus e to the 1. So what's between the red parentheses is 5 minus e. And that's constant, so you can take it clear out in front and do the integral 0 to log 2 of e to the 2x, which is e to the 2x over 2 down here, and then put in those limits, and you finally get to there. So in that way, we have done a double integral by iterated integrals. Now what we will be pursuing tomorrow particularly is that when you have a double integral to do as iterated integrals, it may be that in one order, say you do y first and then x, you will be able to do the problem. in the sense that your recipes from Math 170, like U substitution and integrating by parts and so on, will work. And in the reverse order, you may not be able to do it. In theory, the answers have to be the same because it's the same double integral. But in the practice of using the tricks of Math 170 and Math 175, there may be a big preference for one order over the other. And that's the kind of thing we'll pursue tomorrow. So when your f of xy is not negative, you can interpret how the t became a d there. Anyway, you can interpret your double integral as a volume where the surface z equals f of xy is on top and has region R in the plane as the base. So if you look at problem 24, you have a paraboloid which is given by this formula, and it would, a sketch of part of it would look like this. You see, if you were at y equals 0, so you were in the x, z plane, if you were in the plane here, what you'd have is z equals 16 minus x squared, and that graph would be parabola. Parabola is one letter first power, the other letter squared, like y equals x squared, so on. And you see the maximum would be back here when x and y are both 0, and so it's a parabola like this curve right here that I'm tracing with the stick, opening downward. And in the same way, when x is 0 and you're in the yz plane, your curve would be this parabola. So you have something that looks like this, and your base is the region where x and y run from 0 to 2, 0 to 2. And so the volume, where this is the top, and you have the base down here, which is the square, would be the integral, say, first with y, and then x, thinking of it as iterated. So if you integrate with respect to y, see, you're treating x like a constant. So you're treating the x squared the same way you're treating the 16. So you get 16y, and you get minus x squared y, and then with the y, you treat it like Math 170 as a variable, and you get y cubed over 3. Then you get your limits on y, and so what's left up here involves x and constants. See, after you do your first iteration, what remains is a function of the remaining variable. And then you do this one, 32x minus 2x cubed over 3 minus 8/3 x. Put in your limits on x, and you get the number. Well, let's take a look at the maple here. And you see that if you have something like problem 9, which we did, it's the second one on the first page, you can do double int. If you type the double int with a capital D, then what it does is to print the problem like it would be printed in the book. Remember, with any maple command, if you put a capital letter for your first letter, it is going to print what the problem would look like in the book. It's not going to do it as far as give you the number. if you want the number, you can say value, percent, or you can do the iterated approach. See, int e to the 2x plus y, and then your limits on y, so that means you're doing y first, and then int again, and then your limits on x. So you see that number 8 is the same final thing as number 7. This is a way to emphasize that you are iterating it. And then finally, the int with the capital letters, you see, displays the problem the same way that double int does. So 9 is the same thing as 6 there. Then the next one I have is problem 23, and then the one after that, which is on the front of the second sheet of paper, is the 24 that we just did. So if you look at 24, you can see the maple picture that corresponds to my sketch. So I have plot there, 3D 16 minus x squared plus y squared. And then I've done the double int. The command is 12 at the bottom of the page, and then you turn the page, and you see the setup, and then value, and you see 160 over 3. So that's why I'm self-confident with my answer. So what we will talk about tomorrow then is the more complicated situation where your region might be a triangle, or it might be partly bounded with a straight line and partly with a parabola or something like that. And the problems, the hardest problems, are where you're given the function and the setup for the region, and you have to infer from the limits just how that region looks, and then knowing how it looks, figure out how to rewrite the problem in the other order. And the reason you may have to do that is that the way it's given, you won't be able to do the iterated integrals. You won't be able to do them in the sense of U substitution and integrate by parts, trig substitution to get the antiderivatives. You can do them theoretically, but you may not be able to do them in the sense of Math 170 and 175. For example, sine x over x, you can't do things in that sense of integrate by parts, things like that. But if you reverse the order, what you will be able to do may give you something you can work. So that's where things get tricky. So come back tomorrow and see how that goes.